Welcome to chapter 31, the last chapter that we're going to have on light, which is going to be about light quanta and is going to lead into quantum mechanics. One of the most important things that led in the development of quantum mechanics, even though Einstein didn't particularly like quantum mechanics and he was the one who won the Nobel for this, is the photoelectric effect. What this is that if you take light, you can actually stimulate the emission of electrons by pointing it at a metal object. And then if you place it in a circuit where there's a gap between two metal objects and a battery, then you can get the electrons which are emitted to be attracted and collected at the separate plate. These electrons are then going to have a electron volts or an energy that is going to be dependent on the frequency of light that's going into them. So four things that are important about this is that the time lag between turning on the light and the ejection of the first electrons was unaffected by the brightness or frequency of the light. The effect was easy to observe with violet or ultraviolet light, but not red light. And the rate at which electrons were ejected was proportional to the brightness of the light. The maximum energy of the ejected electrons was unaffected by the brightness of the light. However, there were indications that the electron's energy did depend on the frequency of light. So what ended up happening is that energy was equal to H times F minus the work function. So it was equal to the energy of light that would, given Planck's constant, minus how hard it was to take out the electrons from the material in the first place. So the fact that this energy did not depend on the amount, on the brightness of the light, means that each electron that was ejected by a single particle of light, because if it was dependent on just the brightness of the light, then and it was just a wave, then the electron would have higher energy for high or brightness of light. But if it's just one particle that's ejecting the electron, then it's going to all have the same energy. So this is really interesting, and this states that in addition to being a wave like we've been talking about before, an electron is also simultaneously a particle. So this is wave particle duality, and in addition to being a wave, it is a particle, and what we found was that in addition to matter being particles, they were a wave. Going back to Young's double slit experiment, when you just let one photon pass through at a time, it's going to come out looking like random photons, random particles being developed on the developmental film or the screen on the other side. However, once you have enough of the particles pass through, they start having that wavelength that you expect, or that wave diffraction pattern that you would expect from a wave of light. This means that in addition to being waves, they, and in addition to being particles, they are both at the same time. This is also the case if you do a single slit experiment where you're going to get a diffraction pattern similar to a single slit. And what is really, really remarkable about this and really changed everything, I think, is that when you shoot electrons through a double slit, you're going to see the same properties. You're going to see the same wave particle duality in both photons and electrons. So with matter, wavelength is equal to h over momentum, where h is Planck's constant. But a body of large mass and ordinary speed has such a small wavelength that interference and diffraction are negligible. Rifle bullets fly straight and do not pepper their targets far and wide with detectable interference patches. But for smaller particles such as electrons, diffraction can be appreciable. Finally, for this chapter, before we move on to talking about quantization with matter and quantization with quantum mechanics, we have the uncertainty principle, where the uncertainty in momentum times the uncertainty in position is greater than or equal to h bar, where h bar is h divided by Planck's h, which is Planck's constant, divided by 2 pi. This is interesting, but it's just a property of waves in general, where if you'll remember from the last page, wavelength was proportional to 1 over momentum. So when you have a wave that's 2 pi over wavelength times x, that's going to be proportional to some constant times the momentum times x. This is just a property of waves, but what it means physically is that as you take measurements to find more and more precise values of momentum, then your understanding of where a particle is in space is going to get less and less understood. So as the uncertainty in momentum goes down, the uncertainty in position goes up. And as the uncertainty in position would go down if you were measuring x, then the uncertainty in momentum would go up. This is the uncertainty principle. It can also be seen with energy and time, which the book goes through a way to do it by just relating the work to momentum and delta x and delta t. But another way to understand it is that we establish that energy was proportional to the frequency, or 1 over the period of a wave. This is analogous to momentum being proportional to 1 over the wavelength of a wave, except for instead of looking at position, you are now looking at time. So that property of uncertainty, that property of wave uncertainty that we were talking about being a property of just anything that is a wave, is going to be the same for energy and time as it is for momentum and position.